The broadcast is now starting. All attendees are in listen-only mode.
Oh, okay. So welcome to session 2 of 5 of our technical webinar series. Like last time, this is a reflection of our regional training. My name is Tom Zhang. I'm the Senior Engineer for Optimus Solutions.
I'm Mike Lyons, Eastern District Manager for Industrial Kiln and Dryer.
So some housekeeping from last time on some of the comments. Try to make sure you can see our webcams. If you can see me, if you can see Mike, and if you see the rotary dryer, along with the presentation, it will be very helpful because sometimes what we'll do is we'll go over to the dryer to reinforce a certain concept so that you guys can see. Without further ado, let's go ahead and get started. Okay, so if you guys missed the first session from last week, we do have it on YouTube. If you guys want a link, just feel free to ask us. We'll go ahead and send you a link again. This week, we will talk about mostly the process. It'll be combustion, seal, flights, baghouses, pretty much whatever process questions you guys have, feel free to ask. Okay, so overall, with the process, there are certain quality measures that you have, okay? Certain ways we can define the metrics. The other thing is your particular unit will showcase the certain heat transfers, fluid mechanics, and your chemical processes. So overall, a lot of the baselines you start with in almost all the industries, in the kilns, and the dryers, rotary calciners, and the definitions of that is, again, on the last session. Most questions that people care about are energy consumption, what's the fuel usage, if the process requires on that energy set, what is that, how does that relate, what are the airflows, and how does the energies of the airflows affect it. Efficiency ratings, for me, on kilns is typically energy per ton, such as BTU per ton. Dryers, so one of the interesting things about dryers is it's actually not the production. A lot of people like to say, okay, how much does my dryer produce? But realistically, it's how much moisture we're removing, because dryer, it's drying, it's getting rid of moisture. The better it gets rid of the moisture, the better the performance. The other thing is the moisture is a major energy usage. So if it's energy per amount of moisture, that's actually a better metric, and it's a better comparative metric. Residence time, this is where RPM matters. This is where the amount of time your material sits in the dryer or the kiln matters. Dryers are in the 5-15 minute time frame. Kilns typically maybe even an hour time frame. Again, in the process, people care about production. How much can you make? How much more can you do? Sometimes the depth, how much more you put in matters. The way the flighting is arranged. And again, finally, on the quality of the material or the process, how well you get rid of the moisture, that's a measure of quality. How much yield you get, that's another quality. So these are some of the concepts in the background that I want you guys to be thinking of while we go through each of the components. So, performance metrics, again, residence time, material movement, material interaction with the air, insulation, radiation. What I always like to do is, if you have a metric, can you measure, can you calculate, can you simulate in a lab? That way you can have a quantitative way to know if you're doing a good job. So let's start. Again, this is dryers, or this is burners, flights or internals, baghouses, seals. So with burners, what you'll see is it's quite a bit different, and it goes back to the concept of your dryer is typically convective heat transfer, more airflow related. Your kilns is more radiation heat transfer related, and they do very different functions. Therefore, the burner itself will have a very different function. So a few things, you typically want to know your BMS system on the burners, your burner management system, how well it's done, is it new, is it modern, can you do certain checks, certain maintenance on it, your fuel type. Natural gas is very popular now. I think 5-10 years ago, like methane, waste gas.
I was going to say in some industries, even waste oil.
Mm-hmm. And cement, you got your tires, whatever you can burn in it. Primary air, how do your startup procedures and some of the metrics that we measured, your O2%, your CO, your NOx, etc. So on the burners, you typically on the kiln, you have multiple types of pieces around it. Typically in a kiln is a little bit more complicated than a dryer. On a kiln one, it can be it can be huge. It's pretty wicked. I mean, that's a pretty big unit, and it's all related to how the fuel gets in there, how the air gets distributed in there, or multi-fuels. So.
Sorry.
Someone.
Sorry.
Okay. So for multi-fuel systems, you got natural gas, diesel, coal, pet coke, etc. These tend to be fairly large and fairly complicated and relatively expensive. Whereas on a dryer, kilns think radiation, how that affects the bed, how that affects the heat transfer into the material due to the chemical reaction. On the dryer, your main goal is to get the heat into the air. So what you'll normally see is a bigger fan, bigger combustion fan. You'll have a larger ID in terms of volume of air that goes through. They tend to be simpler. It's a smaller amount of, it's a smaller physical unit, and they tend to be relatively inexpensive. So again, and we're going to go through all the different types a little bit. We're going to be a little bit shallow on the depth that we're going to go. Kiln burners, heat transfer mechanism is radiation heat transfer. They tend to be very large, and a lot of that is the use of many different fuels, the way you shape the air, because the way the flame profile is and the flexibility of the shape, whether you want to make it longer or shorter or more intense, or what we call luminosity, but that matters because all that is related to your radiation heat transfer. On the dryers, your goal is to get the heat into the airstream because your air is doing the work. Hot air is going to evaporate the water leaving the solids, and that's why you have a lot more convection heat transfer. That's why the temperatures tend to be a little bit lower, a little bit different O2s. So on this one, key metrics, O2. O2 on a kiln, you're looking in the relatively low O2 range in the 3%, maybe 7-8% on the lightweight aggregates. Your goal here is you want to be very close to stoichiometric combustion as possible. In terms of the dryers, you'll have more air, so typically your O2 will be a little bit higher. CO, your NOx, in terms of your parts per million, you want to make sure that it's relatively low. Our rule of thumb is about 50 parts per million. This we can do a combustion performance audit, one of the services that Optimus does to do that. Heat mass balances are great metrics to look at your overall process and your overall health in the system. So these are, hey, I got a dryer that's 8% moisture. I'm at 50 million BTUs per hour. What happens if I go from 8% to 6%? Do I reduce it from 50 million to 40 million? In terms of the energy savings, 10 million BTU per hour, is that enough to justify any upgrades or justify any process changes? Is that a $250,000 savings a year if I just let a pile that's really wet sit outside dry a little bit longer? These are where we use data, we use the information from your process to make business decisions, to make financial decisions, so that then you can kind of work your way from an ROI standpoint. Fuel rate, it's an easy comparison on energy. And on the radiation heat transfer to kilns, the luminosity, the brilliance of the flame matters. This is where a lot of the natural gas tends to have a harder heat transfer, et cetera, et cetera. Okay? So on air seals, Mike, what are they not seals for?
They are not product seals.
Right.
We get that question all the time. They're not a product seal.
Right.
There is one that I know of that is a product seal.
And I think I might have a picture.
I think you do. I think I've seen it in the cement industry, possibly, and it's a very, very expensive seal.
Mm-hmm.
But most of your seals, or all of your seal design, is basically just to keep the efficiency of the unit, trap in the air,
Right.
not bring any of the outside air in.
Right.
So,
and the thing is, if you get air from the outside, you're going from 75 degrees or whatever the ambient is up to that temperature, 1,000 degrees F, 2,500 degrees F. You're heating unnecessary amounts of air into it.
right.
Okay.
And also, too, we talked about last time what it does to the material.
Yes.
The chemical changes and things like
Yes,
that.
because if you're looking at 1,600 degrees to change from limestone to quicklime, and you go from 1,600 to 1,550, maybe you're not getting that anymore.
Right.
It's like you're boiling water. Once you hit a 212 degrees Fahrenheit, it boils. If you don't hit 200 degrees Fahrenheit, you just have hot water. Right. Okay, so this is a graphic to show a little bit on the effect. It's not linear. It's an exponential curve in a sense, or cubic, whatever phrase I want to use on it. It's not a straight line. So the bottom here is the amount of excess air. So stoichiometric air is exactly the amount of air to create a flame. Excess air is the air in excess of that chemistry. The left is the temperature of the gas, the temperature of the heat. When you get perfect stoichiometric air, it will typically be very, very, very hot, or adiabatic conditions, what we call it. The more air you put into it, the lower the temperature. So, for example, on a dryer, you may be more here in the 300% excess. This is a direct heat, not necessarily direct fired. On a kiln, maybe you're at 50% excess air. You're maybe more in this range. These are much, much hotter ranges. So this is the typical set, but overall, this can also be used for leakage. The more leakage into it, let's say you're at 50 and you have 25 more. Now you've reduced that temperature even more. So overall, minimizing the leakage. If your seals are damaged on the next shutdown, especially if you have leaf seals, you can just go ahead and change them out. If you have material falling, that typically tells me that you have a material movement issue, how you move that material.
You can have buildup. You can have
buildup.
There's several things that could cause that.
Right.
But it's not the seals.
Right. Typically, it's not the seals because, again, I'm sure, Mike, you get a bunch of phone calls.
We do.
Hey, IKD, can you guys get us a seal? We get you a seal. You put the seals in, material falls out, breaks the seal. Hey, IKD, you gave us crap seals, but we never solved the problem. Right. This is a rough calculation. Okay, so this is assuming 4,500 feet per minute of air velocity, how fast air is going into your system. If you have 180 inch square or whatever it is when you divide by 12 twice in terms of square feet, you multiply that with 4,500, you got about 5,400 ACFM. On a dryer, 50 million BTU type of unit, you're looking at about a 40, maybe a 50 ACFM. So this air leakage is roughly, 10%, maybe 15%, and that starts to add up, especially if you're already maxing out on your fans. I'll tell you a story. We did a frac sand plant. We did a plant that had a combustion chamber, and they were right at the limit. So because they had air leaking into the dryer, they had to increase the ID fan. Well, what happened when they did that was they had an undersized backhouse, Then the pressure went up. Then they have alarms on the backhouse, and then guess what? The operator turned down the fan. Well, when they turned down the fan, the combustion chamber got hot, and then the combustion chamber got melted. So that was a very expensive issue related to seals. Okay.
Right.
And with the seals, I mean, something like that, something so small like that, can be such a detriment. I think that was probably $1 million, $2 million worth of.
Yeah, I remember because I think it did more than just one, if I remember right.
Yeah, it happened twice. Yeah, there was some issues with that. But that's what I mean is, even though seals are a small thing, it's an efficiency thing. Normally, it's an efficiency thing, but it can become much.
Oh,
more.
absolutely. The domino effect. For
Yes.
sure.
Yes, absolutely. Okay, so just a few things. Leaf seals. This is probably the most common. I would say this is relatively durable, relatively inexpensive in a sense, right? I wouldn't say it's the cheapest, but because you have to change the seals out. And we'll have some pictures after this.
You get some flexibility with the leaf seals too.
Right. And maybe 90%. It's relatively efficient. I wouldn't say it's if you have a gas that you don't want to leak even a little bit, this is probably not the seal design. But typically that's what I would say is the most common.
We see that quite a bit.
Belt seals, very easy to install. Belt seals are typically Kevlar. You just cinch it in. It's like a belt.
Yeah, you typically see that a lot in your corn plants and things like that.
Steam tube dryers, things like that. Segment seals, calciners,
absolutely.
carbon blacks, activated carbons, any type of calciner where it's an indirect fire. These typically are meant to put on the reason why is you typically heat up the shell, and the shell becomes pretty deformed, and it will have a lot of run out.
Right.
Specialty seals, there's lots of specialty seals, and I would say these are almost all customized engineering designs. Okay, so just some pictures. I think you have three. So you have a belt seal over here. You got another belt seal here on the left, and another one here on the right. I think this one's one of those where it catches the material.
That's the one we were talking about that I've seen, that we kind of see typically in your cement plants.
Mm-hmm. And then this is another belt seal with some extra loops to cinch it a little bit better. On the left here, these are what we call the graphite seals. They tend to be very, very tight on the design limits. You typically don't want a lot of run out, but they do a very good job sealing.
Would you see that maybe more on cooler type systems?
Maybe a cooler, or maybe like a specialty kiln or a specialty dryer. Because typically that's quite expensive, and you have to be very, very careful on the air going in. So maybe some special chemicals. You see some leaf seals here, some additional leaf schematics here. This is, I think, a Webco seal with some of the cinching with the cables.
And those types of leaf seals like that, what you'll run into, especially if you do get any backup or you get a piece of material that gets stuck in there, it could rip a lot of those off.
Right, because they're bolted on both sides. Right, I see. Okay, so we talked a little bit about burners. We talked a little bit about seals. We can talk a little bit about the airflows. So the main point here is you got primary air. The main goal a lot of times of primary air is to mix the fuel and the air. Because if it is mixed, it just burns. If you don't mix it, because you get the flame triangle is normally fuel, air, and an ignition source. If you don't have air, you don't have flame.
Right.
It's just smoldering. So in this case, air, you need it to mix. So primary air is typically a way to mix. Secondary air is where your ID fan comes. This is where it pulls that air through your system. When it pulls that air through your system, this is where it can help shape the flame. It can help, and some of the more complex burners can do that too. And then again, on the dryers, it's there to pull as much air out as possible.
Right.
So these designs will be a contribution into your specific unit. So the radiation, heat transfer, convection. Like I said, and I'm going to hound this many times, is that kilns, radiation, heat transfer, dryers, convection, heat transfer. Because that is one of the core mechanisms, and that is why the units are designed the way they're designed and the way they are run and maintained the way they are.
Well, two different drying processes.
Yes, right. So kilns, you want to remove the combustion product, you want to get that air through. In terms of the air's role, you want to keep the balance of the fuel and air ratio. The goal of that air is to keep it's a balance in a kiln. Okay, it's there to keep the flame as hot as possible, get just enough to get all the air out, but not so much that you get too much dust.
Right.
And it's still there to remove the dust and all that. On a dryer, on the other hand, it's almost a full-blown lot of air because that's the job, right? So if you see that example at the bottom, your BTUs go in, your BTUs exchange with the air. That's the truck itself. BTUs go get H2O. So that's on a dryer. That's the job of the air. Without air, if your ID fan's out, you can't do anything. So air is a very critical role. A few metrics. You'll see CFM. You'll see amp draw. You'll see percentages. CFM is the best way to communicate if you have an air problem. Hey, Tom, we got 40,000 CFM. It used to be 60,000 CFM. That's very helpful because then if we do a heat mass balance, I typically get a CFM out of it, and I can do a cross comparison. If it's an amp draw or a percentage, I don't know what I'm comparing it to. If I know that amp draw, like 20 amps, is equal to 30,000 CFM, okay, great, now I can use that.
What do you think some of the reasons could be? Just a few, if you got any examples of what could cause something in a big drop like that, going from 60 to 40?
Oh, the easiest one is your baghouse plugging or some kind of dust collector plugging because it's so much pressure that you can blow the bags. So then you would actually lower that to relieve that pressure a little bit and then go back up. So a pluggage.
Have you ever seen anything like in a damper?
Yes, you could close that damper and it'll raise or lower your CFM. Typically, you would like to have those as automated as possible because any little thing you change into the system will change your flow. It's like in your house, your HVAC. If you close all the vents, you got more air coming out somewhere else, but then you may change the pressure drops. This is how much it can move the air. That's the other design metric that we run into.
So something as simple as even a damper could cause.
Yes, and that's the thing is a process is is typically very well balanced, and any little things can upset, and that's where the residence time comes back in on a kiln. On a kiln, if you make one change and then you make another change and you make another change, and it's all within an hour, then you may have a whole slew of problems an hour later because the stuff that you see in the beginning may not be the stuff that you see at the end.
Right.
Okay. Okay, so internals. So these are some of the interesting pieces that we can talk about. So internals, the main functions of them are multitudes of functions. Residence time control. If you have stuff going in and you want to slow it down or you want it to be at a certain section, this is where dams are useful. If you have material movement, you need spirals to move it in terms of conveying it, axially conveying it towards the discharge.
And even actually on spirals, even some of your combustion flighting, I have seen what the industry calls kicker flights.
Yes.
To help move the material.
Right. If you have combustion flights and you don't have kickers and it just sits there, you probably need to look at putting the kickers in or some way of moving it forward.
And then actually on the dams, you may even see multiple not rows, but I guess sections of dams in there. And depending on the height, a lot of times, as you were talking about making changes, a lot of times even with your dams, taking out just a section
that can affect
a segment. Just one of the segments could make a huge difference in your material flow.
Absolutely. Then you got mixing flights. They're there to break up clumping that you have, and lifting flights. These are very common in rotary dryers.
And then that helps with the veiling process. And,
Yes.
and a lot of times you see this in dryers for picking up. Occasionally you'll see something like that in a hybrid of a half kiln, half dryer.
Soda ash is a pretty common set like that. Refractory, these are mainly in kilns. It's there to protect the shell and to bounce back the radiation. So this is like you build a wall in a campfire to kind of push that heat back into whatever you want, either the food that you cook or the people that you want to keep warm. And then chains, this is more common for your open paper mills, some of the older wet kilns, so your 6-pier or more or 5-pier or more kilns. So let's go a little bit more detail into it. This is the axial flighting mat. So what it is you take a circle or you take a cylinder and you flatten it out. I would say this is a fairly common design set for a direct heat, not direct fire, direct heat unit with an inorganic. So not corn, not beans, maybe like a some kind of aggregate, some kind of sand.
Yeah, just there's, from what I can tell from the diagram, there's just not a lot of lifting.
Well, the lifting's kind of and towards the end. It's kind of hard to see. So I'll kind of describe it. Sure. You'll have the mixing flights or the spiral flights on the left. These will typically, in your second row to the right of it, this on my mouse here is, say, your mixing flights, and all of these are lifting flights.
Well, and I guess when I meant lifting flights, I guess I should have clarified. I meant more of a aggressive type.
Oh yeah. This is like an L shape with that.
Correct. Yeah. So there's not as much of aggressive picking up and veiling through the
right. And speaking of lifting flights, this is a lifting flight that's, like you said, a little bit less aggressive. It's a little bit more gentler. The thing on the left, this is probably a stainless steel unit, so they probably need a lot of anti-corrosion types of property in the unit, and then this on the right is looks like a normal carbon steel. Right. Sawtooth, these I would say are more aggressive, right? These you try to lift and say on the L shape, you may get it up to 12 o'clock, maybe to 11 o'clock. The sawtooth, you can build it even more aggressively. Right. So the sawtooth is like a J flight plus a L flight altogether.
And that's one of the things that we can help a lot of people out too with the process is helping design a high efficiency flighting system.
Right.
Using, getting involved with the process side, we can help develop, because, a lot of times, depending on the process, there could be a mixture of sawtooth and L flights in a row, just depending on the process.
Right.
And it's something we do a lot of to help people.
What's interesting is you can overflight. If we hold that thought, I'll have more comments on that. Sure. You could overflight a unit. You could have too much flight, and that actually causes other issues downstream. And again, the major point throughout this presentation is everything is linked. The burner is linked, the flights are linked, the airflow is linked, and eventually the backhouse.
Well, they're all handcuffed, that's for sure.
It's all handcuffed. If one fails, the rest of the system fails. Spiral flights, this is meant to move the material forward. If you have seal issues, one of the first things I have a discussion on is this. Or your conveyor. If you have a conveyor and it's just dropping material down into the unit and it's just dropping into a gap, you probably need to move that conveyor to where it doesn't do that. Both of those are reasons for seal problems. Combustion flights. You want to take a look at the unit so that we can kind of show. If you guys, before we move over to the unit, make sure your webcams are on where you can see myself, Mike, and the unit. And what we'll do is we'll go ahead and close some of the screens to where you can see the unit so we can show you kind of roughly where all this would be. So let's go ahead and do that. So I'm going to turn off my webcam. I'm going to turn off the presentation. Mike's going to turn his off. So you should see the unit. Okay, so this is for the dryers. Let's see here. I'm going to go up here. Mike's tall, so we need to do that a little bit. Oh, there we go. Okay, so let's say this right here is your feed end, and that right there is your discharge end. Your spirals will typically be over here. If it's parallel flow, so you're feeding this way too. And this is going to be for a dryer. If it's still kind of wet, your material's still kind of wet, still clumpy, this is where the mixing slides. And I'll show you the mixing slides in a little bit. So this will break up the clumps, and then almost all of this over here will be your lifting slides, your Sawtooth Flights, et cetera, et cetera. And then sometimes maybe over there at the end, another mixing slide if you want to gently convey it back out. And that is for a direct heat unit, so your burner's over here, okay? If you have a direct fire, your burner's going to be in here. So this is where the combustion flights are lined up over here, right? To where then you protect the shell a little bit. Now in a kiln, what's different is instead of combustion flights, you just have refractory throughout the whole thing. So that does the same job as combustion flights, except kilns are much hotter. So you'll probably melt the combustion flights, put it in a kiln, or the refractory will survive.
A lot of times too, you'll see in between flights, you'll see some little square bar to kind of help keep the material from sitting on the bottom.
Oh yeah. So one of the things, one of the tricks that we can help you with is if you ever go inside a unit, and this is applicable for anything that's bare metal, so with your dryers, maybe with your calciners, right? If you ever go inside a unit, if there's a very, very shiny spot, that means you don't have just even a little angle iron or quarter by quarter inch, anything. Because what's happening is, let's see here, it's doing this motion, and then if you keep doing this motion, you have the material doing this, sawing back and forth. It's like sandpaper. Actually, if there is sand, it is sandpaper. Right. But if you have something like this where it hits and it goes over,
Helps tumble it a little
it helps tumble a little bit, so that should improve your life. So one of the things I always look for is if there's a shiny spot, you've already screwed up. You need to go ahead and put something there, a little piece of angle, maybe throughout.
A lot of times just some three-quarter,
quarter, whatever it is, just to break it up. Because if you keep doing that, eventually the shell will thin out. We'll again have two pieces. Okay, so let's go back to the presentation. Okay, so we talked a little bit about the combustion flights.
Actually, you kind of see there on the.
Oh, right here.
Yeah.
That's the angles that you were talking about. And on this one, the kickers are under it, and on some of them, the kickers may be on top of it. So you'll see right here, you can see a little angle there.
Just a little bit, yeah.
Little bit of a kicker right there. Okay, so these are typically for direct fire. So if you have a direct heat unit and you have combustion flights, then you're kind of missing out and you need to do some changes. But typically, that's not common. This is mixing flights. Typically, they're flat, different designs. They're there to break up any clumps. Okay, they are not necessarily there to veil. And damage flights. Okay, so I got a story on this one. I was somewhere south of the border. This customer, I think this is pozzolanic ash or pozzolanic rocks or pebbles. And they called me and they're like, "Hey man, our dryer is not working." I'm like, "Oh, what do you mean?" I was like, "Yeah, we put in 50 million BTUs, 70 million BTUs, and we're not drying. It's not working like it used to." I was like, "Oh, okay. Well then let's take a look." So I went down there, went inside, and I was like, "Hey guys, you need to put some flights in." And they're like, "No, we don't need to do that. We need a new burner." I was like, "You need to put some new flights in, because if you have something like this again on a dryer, you want to fail, it's not going to fail. It's just going to.
You're not moving the material
You're
at
not
all.
moving the material. You got all the. Actually, this one's a different unit, but you got. you have a kiln in a sense, because it's just all going to slosh at the bottom. So my recommendation was put in new flights, and this is an extreme case, but it is out there.
We do see it.
We do see it. Damages. So something like this indicates maybe the bed is not high enough. Typically, if you have it where the bed is higher than that at the bottom and the material falls, you won't see it. This happens. This design is it's more of a bucket mechanism and all that. But yeah, more on the damaged flights. People like to see what others are that are damaged. Okay, so that is the internals on flighting for, say, most dryers and calciners, if any.
Well, you're going to get the different arrangements based on the process.
Exactly. Refractory. You got different terminologies: refractory, brick, castables, and they all mean different things. Okay. Refractory typically is in the style of a brick. I think I have some later, where the goal of the refractory is to protect the shell. If you have any misalignment in your burner, where the burner nozzle is into the refractory and, in a sense, melts it, you'll have something that you will see on the right. Typically, that'll be in the discharge end, really hot, where the burner is not aimed right. So this is where an audit's good. Have your burner guy tune it to make sure the angle is right on the kiln. We provide that service too. You don't want a hot spot. Typically, that's a shutdown situation. Right. Very dangerous. If you have bad refractory, that typically causes mechanical problems. That's where we go back and you should do an ovality measurement. We actually are going to have a small session on ovality at some point to discuss details on that. But ovality is a very good check. You can do it running, and that is normally for refractory. So all ovality is it's got the word oval. The opposite of the perfect ovality, the perfect oval, is a circle. If you have a perfect circle in the kiln and you brick line everything with brick, perfect circle, so it's not going to break. If you have a oval and it does that, you build an arch and you deform it a little bit, everything falls down. That is ovality in the most basic, generic sense.
And that's something you can get done on a regular basis too.
Yes, absolutely. Okay, so on kiln refractory, you have, so this over here on the bottom is a kiln dam. This is actually pretty big. I think this particular one was about 45,000 pounds. It's actually a lot heavier than it looks, but in a sense, it's really not that much compared to a kiln, which is maybe 1 million pounds with all the refractory in it. Main goal here is to change, let's say you want a dam at the discharge end, you want to keep that material a little bit more close to the burner to heat up. This is where a dam is helpful. You got a lot of different refractory types. Some of them are basic, what I call a basic refractory, so your magnesiums, and then you got your aluminas, and this is where all your refractory groups can make different recommendations based off of a chemical reaction or conductivity. So if it's good conductivity in terms of, hey, it's not so hot here, so we can get away with a lighter brick, okay. Or you change thicknesses. I mean, you've seen it, right? People change refractory thicknesses. When you do that, make sure to look at your loads. I think I talked a little about it last time. You did. Make sure to look at your loads, because on a kiln, your major source of weight is your refractory. On a dryer, a lot of your source is the material itself. Right. So comparison, kiln, a similar BTU kiln is maybe 30 tons an hour. Similar dryer may be 200 tons an hour. On a kiln, it may be 200 feet by 9 feet. On a dryer, it may be 8 foot by 30 feet. So it's a very different set for the same amount of energy. Again, old, worn brick, you'll see something like that. But really, I would say most people don't have a lot of opportunities to go inside, do inspections on a refractory. So again, the for refractory, ovality is a good measure. Ovality is a good measure. And then some of these, if you get to the certain point where you need to put castles, okay, try castles. Otherwise, on your lime kilns, your cement kilns, they call those what, a coating. So this is your material still building and coating on top of the kiln. So that's something that also helps on the insulation. Refractory is the same thing as a ceramic plate at home. Okay, now I've done this because I've been lazy, is you heat up the microwave, I got something I want to cook, instead of putting it in an aluminum pan, I put it on the plate, heat it up, take it out, wash it, and the plate breaks because I have not given that sufficient time to cool. It's the same idea in a kiln. If you cool it too quick, the refractory won't grow or contract at the same rate, and then you'll have a whole bunch of refractory breaking apart. That's why in the kiln.
That's why you have the cooling process and the warm-up process of the kiln.
24, 48 hours. Right. It's longer. But on a dryer, if you got a direct heat where you got the combustion chamber, that typically has refractory also. That causes issues if you don't give it time to heat up and cool down.
Right.
Okay, that's why this is a critical spot. Otherwise, you just get a lot of issues. Again, the ovality is the major part of making sure your refractory stays in tip-top shape. There's certain limits on it. Make sure that you do that, say, whenever you do an alignment check, whenever you do mechanical measures, diagnostics, go ahead and make sure you get ovality on it.
Here's a question. What is the recommended heat up and cool down duration?
Typically on most of the kilns is 24 to 48 hours. Okay. The past 5 companies I've chatted with on it, they've been more on the 48-hour side. 48 to heat up and 48 to cool down. Okay. Chains, okay? I think I wrote some on chains. So chains are normally on the feed end of kilns. Very, very common in pulp and paper. The reason why is pulp and paper is still a wet process. What that is it's a wet slurry. When you have a wet slurry in there, the chains are there to add heat into the slurry to try to evaporate the water as fast as possible. Okay, they're more robust than lifters, and also when you have lifters, you're just throwing water in the air, so it makes it a little bit harder. So that's why the chains, actually, you heat the chains, and the chains go into the material to heat the material. Very common in pulp and paper because it's a slurry. A lot of the cement kilns now have moved away from chains. It used to be wet kiln processes. So actually cement, it used to be 5 piers in that range. Then they got rid of this. This is now in typically a preheater tower or pre-calciner tower, and now it's a shorter set.
Yeah, there's another question. What is the recommended maximum ovality to avoid refractory damage?
That depends on your diameter. So my rule of thumb is, let's say you have 10 foot, okay, 10-foot diameter. 10-foot diameter, I like to go ahead and convert over to meters. So 10 foot is roughly 3 meters, right? It's 0.1% of that. So for 3 meters, 0.3% ovality is your upper limit, okay? That is a general rule of thumb that I've used that has been relatively good so far. So so it's dependent on your diameter. Also, you do have a bottom limit. So if it's and this is more on your creep. If you have 0 creep and your shell's expanded, then you can cause damage by plastic deformation or coat modeling on it. Again, chains are heavy. Refractory is heavy. And design on these units are very close to the limit. And typically this is in the Pier 4, Pier 5 range for chains. So for this example, customer wants to change chains. Or this is the, in this case, it's the new chains. Okay. Hey, I got new chains. Okay. What's the weight of it? It's extra 45,000 pounds or extra 100,000 pounds, whatever it is. Okay. Am I good? Okay, let's see. So in this case, your tire bending stress is load on the tire now. It has exceeded 10,000 psi. That's a general rule of thumb. I float between 8,000 and 10,000 psi depending on the particular unit, etc. And this exceeds both. So what this tells me is that you need to consider the weight. You need to either beef up your tire, which is not easy. You need to beef up the rigidity of the shell, which is not easy. Or you may not be able to have that kind of chain in there.
Well, what about, what else would it affect besides the tire?
The rollers, the base, the piers. You got to remember, these are massive machines, and especially with the last, I guess modern kilns, with the technologies that we have and the cost cutting that a lot of OEMs have, they've designed it as close to the limit as possible. So now any wiggle room you now may exceed. Okay. One of the things that we're trying to do is make sure that if it is that limit, if we all agree as an industry that limit, can we prove it with engineering principles? If it's a rule of thumb, like the Old Valley, that's a rule of thumb. That's a rule of thumb. If it's a straight physics-based limit, this is a limit and this is a fact. Thing we all aspire to get better at. Yeah, load consideration. This one is a very, very common one I see. So if you guys have chains and you're wanting to switch it out, let us know. It's a 2-week study. It's pretty fast, and you'll know versus you'll instead of guessing, because this is highly consequential if you screw up. So, I mean, we're talking a lot of different internals, a lot of different industries. So sometimes it's relevant, sometimes it's not, right? So the other one, the indirect or the direct, indirect dryer is a steam tube. You are heating steam, and the steam heats the steam tubes, and the steam tubes heat the material. Very different heat transfer mechanism, very different design. Your steams is your major component of steam tube. These are coated pressure vessels. So if you're not doing the proper inspections with, I guess, a coated shop that does the maintenance on it,
right,
then you need to make sure that happens. You need to make sure that the right pressure is on there. You need to make sure that you got certain tubes that leak, and then they'll what do you call it? They'll close it off, or they'll panel it off.
Right.
Now, just remember.
Basically, they'll just block it off.
They'll block it off. Just remember, though, that if you have a steam tube dryer, let's say you have 100 tubes, sure, and you have 100 or 10,000 pounds of steam. That's roughly 10 million BTU per hour. That means, or let's make it easy. Let's make it 100 million BTU per hour. Okay. If you have 100 tubes and 100 million BTUs, each tube is 1 million BTUs. If you block a tube, you're going to decrease your production, okay? So if you block off 10 tubes, you went from 100 million BTUs now to 90. If you block off 50%, you have 50% of capacity. So just remember that if you block a tube, that doesn't mean you get the same heat.
Right, you're basically just killing the efficiency of the unit.
Yes, yes, absolutely. There's another view. Hot steam goes towards the, let's see here, towards the discharge, and so the left is discharge, the right is the feed. And then there's a siphoning effect as it goes through to get the water coming back, and then the water has to exchange out. So it's effectively a giant heat exchanger in the heat exchanger sense. Every one of these units are heat exchangers, okay? Steam tubes are always unique in that sense. So finally, we got some time left. Dust collectors, primary dust collectors, secondary dust collectors. Primary are your cyclones, your knockout boxes, and your secondary are your scrubbers, your wet scrubbers, your electrostatic precipitators, and your baghouses.
So now with your knockout, your primary collectors, I mean, is that, what's your purpose for having that?
So this is kind of like your big hit. So you got a whole bunch of dust coming out. You got a knockout box. It's very simple. Both of these tend to be very simple mechanisms. So you should get a lot of stuff with a relatively inexpensive compared to the other ones that are less sophisticated where it's simpler. So then it can achieve a lot. And then your secondary are kind of like your fine powdery
200
mesh or whatever. And the thing is, this is more for environmental.
200
so,
fines.
Yeah, fines. So something like that. So cyclones and knockout boxes. Cyclone, this is actually the inspiration for all the Dyson vacuums. That's what that dude saw. You got particulates coming in, you got exhaust gas going up, and it rotates around and it falls to the bottom. When it falls to the bottom, you open the gate and you get the stuff coming out. Sometimes you sell it, sometimes you get rid of it.
Well, I was going to say, a lot of times it's even just put right back into the...
Yes, put it right back into the feed or sell it. Knockout box, similar mechanism. It's a giant flat plate, and the material hits it and falls.
Or sometimes you'll even see angle iron used in
that,
like a grate. So,
right. Both of these are very simple. They typically don't have moving parts.
Correct.
Okay. Yeah. Any comment?
No.
Okay.
Just
your
simple design.
Right. Simple design. Your secondary collectors are a little bit more complicated. They tend to use some active mechanisms. Your electroprecipitators, electrostatic precipitators use your charges. So it charges the particulate and it sticks onto them, and then it discharges, and then it releases it. Your wet scrubber, the material coming in, you got water flowing through, and then the water catches it or the fluid catches it. In your baghouse, you have bags, I guess the other version of the vacuum, So you have the bag that sticks on the bags, and then it pulses to move everything down.
Correct.
So all three of these are more sophisticated.
Correct. Again, just different processes. But I know one thing: you definitely don't want to be on the end of changing out bags.
Yes. Actually, that reminds me. So remember when I said overflighting? You can overflight. When you overflight, you can lower the exhaust gas temp. If that is too low and you got a lot of water, you will do what we call mudding the baghouse. And I have not done the change, but I have never heard anyone that enjoys changing those. That's correct. Okay. So some design considerations for baghouse: particular size, your material. This is for temperature and expense and air to cloth ratio. These are some suggested air to cloth ratios for that particular industry or for that particular type of fines. Typical, like I said, you either overload or you mud. Okay, if you mud, typically that really sucks, and you have to clean it all out because once it clumps onto your bags, you really don't have a baghouse anymore. Overloading, you have the possibility of damaging the bags, and once you damage it, all that dust comes out, and you got emissions problems. Okay, so overall, from this journey, I think I'm good on time. Your heat transfer mechanism is determined by the kiln and the dryer, meaning, it starts with radiation or convection. That determines the equipment. That determines everything else on your burners, your airflow, your seals, your internals, your baghouses, your secondary dust collectors, your primary dust collectors. Everything from this discussion, and this is a very, very light discussion. We can go very deep into it. Everything's interconnected. If the burner fails, you can't do anything. If your baghouse fails, you can't do anything. If you have no internals, you can't do anything. If you have no airflow, you can't do anything. Okay, maybe you could do some on the seals, but we saw that it was $1 million problem. Some issues on it. So that is kind of the main topical points. So if you have any deeper questions, feel free to contact us, industrialguild.com. Go to the comment section. You can ask some more questions. If you guys have any questions, let us know. The session one's done last week. Session 2 is now done. Next week, next Thursday, is Session 3 on the mechanical systems.
I think we're doing that one. You and I are doing that one. You got some other guests coming in for some of these other ones.
Oh yeah, okay, yeah. We got some cool stuff we want to show throughout. Again, with the current time, with the current pandemic, you guys are essential businesses, and so are we. We're here ready to help. We're here. We're open. And you got any other questions? You guys got any questions that you guys want to go? Well, if there's no further, you have a question.
I'm good. I think we covered a lot of stuff.
We did cover a lot of stuff. It is a lot of stuff. Okay. So again, we appreciate the time with you guys. Thank you. This recording will be posted later, and we will send the link out to you guys. Well, again, appreciate it, guys, and
Stay safe.
Stay safe.